let us conclude this important inequality. So this is something quite remarkable, right? Because we have, we are considering the wave equation in any domain, right? So as you know, there is an important wave process ongoing that we can understand either by the rays of geometric optics, or if one prefers, as vibrations described in Fourier series. And it turns out that, by a rather simple proof, simply using multipliers and integration by parts, we are able to show that boundary observations, right, are able to recover the energy inside, right? And of course, this is very much related to the theory of inverse problems, where the goal is precisely to recover information about a medium, inside, out of measurements done on the boundary, right? And this is the basis of many of the medical applications, like, scanning, tomographies, PET, etc., right? So we have all seen these images in which, for instance, one can get very clear pictures of our brain or any other organ or bones inside, out of signals taken from the exterior, right, boundary. So this is precisely one of the starting points of this relevant topic of inverse problems for wave equations. This is, of course, very important as well when you are considering the search and the management of, natural resources like oil or water underneath, right? So we are sending signals from the surface of Earth in order to detect what is inside. And you see that the principle, just a small discussion before I get into the proof, right? The principle of this kind of inverse problems or inverse problems resolution techniques is precisely that in case, right, is more or less what we said yesterday, right? So you are trying to analyze what is inside this medium omega, to which you cannot penetrate, right? So you live here on the boundary. So we are living here on the boundary of this domain outside, right? And we wonder what is inside. So is there water, petrol, granitic rock, whatever? So the principle is that you say, okay, fine, in case, right? In case I send a signal, right? In case I send some kind of pulse ray, right? It will penetrate the domain, right? And in case the medium is homogeneous, this ray will, exit the domain on the other side, right? So in case this set were empty somehow, right? You will send a signal here, and then you will see something coming out over there, right? Actually, you could even, according to the travel time from here to here, you could also measure what is the medium under consideration, right? Because if you consider this wave equation here, where the coefficients are the unit, right? Then you can always say, oh, yeah, then, the coefficients of your equation are 1, the velocity of propagation is 1. But when you change the coefficients, you change, for instance, the density here of the wave equation, then the velocity of propagation changes, and then this travel time, right? This travel time, that is something that you can record, right? Travel time will give you already information about the medium that you are trying to disclose, right? But it could also happen that this medium is not homogeneous, right? So this medium could be, perforated or could be occupied by heterogeneities, rogues, for instance, inside of some kind of, tumor or defect, in case you are thinking of some medical application. Then what happens? Then what you really expect is that when you send a signal, right, this ray will travel, but, when getting to, this obstacle, it bounces, and then rather than recovering the exit of this ray where you expected to geometrically oppose here, you will get it over there, right? So then the fact that when you send a signal in this direction, you recover, the outcoming, component of the signal over there, immediately tells you that there is something here that in principle is not compatible with a clean, homogeneous, right, medium. So this is why, as I said, this kind of inequalities, although very elementary, is very much related to this theory of inverse problems, in which the goal is to identify properties of an unknown medium inside out of boundary measurements. As usual, as Norbert Wiener said, right, you need somehow actuators and sensors, right? So you need actuators in order to be able to produce these signals, right? And you need sensors to recover, right, the outcoming signal. The geometry of this map, right? So what is the input-output, pair of points, plus the travel time, right? This gives you plenty of information of what's going on here inside. In particular, it will immediately detect whether the medium is homogeneous or is heterogeneous, right? If you see that, the input-output map is simply being some, along the diagonals, then you will immediately say, well, this material is homogeneous, right? So we don't know exactly what it is, but they can tell you it is homogeneous. But as soon as you see that array breaks, breaking meaning that it doesn't really continue along the diagonal, but it really, is twisted in the sense that the output point is not the diametrically opposed one, then you can immediately deduce, the domain, the medium is not homogeneous. So there is some heterogeneity on it, and we have to analyze it further. But you see that this principle, if you continue applying it, right? So once you detect that, through this ray, I have observed that there was some kind of heterogeneity there. Then once you realize that there is something there, then you can continue sending, rays, right? And in this way, and in this manner, you will be able to reconstruct the geometry of that, obstacle, right? So you will continue bombing, right, the obstacle with rays, record for each, incoming ray, the outcoming signal, and, revisiting, all these possible ray directions, the output of these ray experiments in the different directions, you will be able to recover the geometry. Okay, so then you see that with these basic principles, input-output operator along rays, you will be able to observe whether a medium is homogeneous, whether there is some inhomogeneity, and in case that there is some inhomogeneity, what is the size, what is the shape, what are the materials, and all this. Okay, so of course this becomes a whole field. This can be rather technical, but the principle is exactly the one I told you, right? Okay, so and why this observability inequality is related to, this kind of inverse problems? Well, it's simply because, this is the basic inequality that is telling you that indeed, all these make sense because you can recover fully the energy inside the domain out of measurements done all along the boundary. Okay, so of course, this kind of technology based on ray analysis is more micro-local. This is rather a global observability inequality, but is at the heart of the principle that, there is hope that you can recover everything inside simply out of boundary measurements. As I said yesterday, the proof is very simple. It's just based on the multiplier's identity, which is very much connected also to the theory of Kalman and hypoellipticity, which tells you, listen, on systems, oftentimes the different components of the state are rather mixed. And if you want to, to see the true effects of control or damping operators, in this case, observation operators to emerge, you have to cross the different components of the system through these B star, A star brackets, right? So here what we said is, we multiply the equation by x gradient u, and then integrating by parts without any difficulty, carefully we got to this identity, right? In which I said, well, everything looks nice because I see here, the kinetic energy. I see also the potential energy, and I see also the energy measured on the boundary. So I have the three ingredients that are needed to prove the observability inequality. But I made a warning in the sense that, listen, be careful, because here you have d over 2 and 1 minus d over 2. In dimension 1, this is fine because d over 2 is 1 half, and then you get here 1 half and 1 half, so you get the energy. But in dimension 2, the potential energy disappears, and that was our goal, recover also the potential energy. And in dimension d greater than 2 is even worse because, the contribution of the potential energy is negative, right? Okay, so we have to work a little bit more. Well, of course, the first remark to be done is, well, so here, I could also always say that this is less than r over 2, the integral over the boundary of the normal derivative squared. Right? So I can get rid of this multiplication factor. It is really not that important, right? I can get rid of this. Because x times mu is constant. So why is that true? This is simply related to the fact that if you ask me to get a bound on x times mu, I know I have, the Cauchy-Schwarz inequality. Mu, by definition, is the normal unit vector. And what is the norm of x? Well, so we have a domain omega, right? Assume the center of gravity. There is no symmetry on this domain, right? So the center of gravity of this domain could be anywhere, right? And, the origin is here. So when you look to, to x, you can always say that this is less than r, where r is the maximum for x belonging to omega bar of the, of the norm of x. And what is this radius? Well, this is the radius of the, the distance from the point in omega, which is farther away from the origin. So this will be the radius of the ball, right? That contains capital omega. Of course, if the domain capital omega is bounded, this disk is always bounded and such a constant r exists. Then, of course, you could also play, once you realize this, you realize that you could have, rather than working with the multiplier x gradient phi, we could have shifted the center of gravity, right? And make computations with center of gravity somewhere else, like for instance here, right? And then achieve the same kind of computations with r prime, right, of x0 less than r, right? So you can improve, if you want to, you can improve the constant here. But this is not our goal. So this is fine from this side. My main concern is here. So what do I do, right, with this term? So, and here, we use the equipartition of energy, right? So what does it mean? It means that, you see, when you take the harmonic oscillator, we said from the very beginning that, of course, we know that the solutions of this harmonic oscillator are simply, very simple complex exponential trigonometric functions, right? And we know also, multiplying the equation by x prime, that the energy is constant. So this is an harmonic oscillator in which there is no dissipation, a pendulum that will oscillate with the same amplitude, the same velocity all the time, right? So we also know that drawing the trajectory of this pendulum on the phase plane, right? The trajectories are circles, right? And then if you ask me, how is the energy split into the kinetic component and the potential component, I will tell you, well, there doesn't seem to be any rule in principle, right? Because you see, when you are here, x is maximized, but x prime is equal to 0. So it means that when you are passing by this point, crossing with the horizontal line along the trajectory, all the energy is concentrated on the potential energy, on the potential component. While when you are passing by x equals 0, right? So when you cross, the haze, x equals 0, then x prime is maximized. So all the energy is concentrated on the kinetic component. So the complete energy is conserved, but there is a dancing, right, in which the energy is being transferred from one of the components of the energy, kinetical potential, in a completely, say, harmonic manner, right? And this is what the pendulum does, right? So when you get, to the maximal angle, then before the pendulum comes back, recovers, the way back, there is a point where the velocity is equal to 0. And this is in this maximal angle where the maximal velocity, where the maximal potential energy is accumulated. And it's this potential energy that, pushes the pendulum back when passing by, the vertical equilibrium, is when the velocity is maximized, the kinetic energy is maximal, and this kinetic energy pushes the pendulum up again to the maximal amplitude oscillation before coming back, right? And this is a completely periodic motion. You see the period here is 2π. So you ask me, can I say something about whether the energy, the kinetic and the potential, the two energies are related? I will tell you, well, not really, because, I will have to distinguish whether you are passing by the equilibrium, you are in the other extremal case. There will be also intermediate situations where the energy will be half and half. What can I do? Well, you can always do this argument of equipartition of energy that says, well, it's true that if you look at things on a given time, you can say nothing. Why? Because, you can be either here, here, or here, and the picture is completely different in terms of the distribution of the energy on the two components. But if you rather look to segments, then you will see much better, right? So the argument says, multiply the equation by x, right? So you see again the same kind of computations we did, and then integrate from τ1 to τ2, right? So this is obviously true. Given any time interval, 0, τ1, τ2, finite, short or long, you can always do this, right? And as I said, this is the kind of arguments we use in hypoellipticity to show, to build, for instance, the Lyapunov function for the decay of the wave equation. Now, when you see this, what do you say? Well, so here I have the potential energy. This is a non-symmetric term, x double prime. but I can make the kinetic energy emerge here very easily, integrating once in time. So when I integrate once in time, I will have the integral from tau 1 to tau 2 of x prime squared dt plus the integral tau 1 to 2 x2 squared dt plus the product of x prime tau 1 tau 2, right? And this is equal to 0. So this means that basically, when you look to, the potential energy plus this remainder term, right? This will give you precisely the kinetic energy. So this is the kinetic energy, and this is the potential energy. Okay, so this computation is telling you that if you focus on, the kinetic energy and potential energy accumulated during a time interval, then you can say that one is equal to the other, right? Up to, to some, right, remainder term. For instance, if you were integrating the energies in this arc, right? You see that in this arc, tau 1, tau 2, at tau 1, x prime is equal to 0. So this goes away. At tau 2, now when you are here at tau 2, x is 0. So this term goes away also. Then you could say that the energy accumulated here is identical in the potential and in the kinetic component, right? So if you take a double arc like this, you will have the same. Why? Because integrating from tau 1 to tau 2, the cross terms will go away because, either one or the other will vanish. The same will happen when you do 3 arcs of circles, okay? Of course, if you take a very short piece, these two quantities will not be exactly identical. There will be, but you can still, right? You can identify what the gap between the two energies is just looking to the extremal values, tau 1 and tau 2. Okay, so the same computation can be done for the wave equation, because when I multiply the wave equation for the adjoint, I multiply by 5, and now I take the scalar product. In this case, this means integrating on time and space. Then when I get is this. Is equal to 0. When I integrate here by parts, I simply get the gradient of phi squared dx dt, right? And when I integrate by parts here, passing one time derivative from phi tt to phi to make it symmetric, what I get is here minus the integral from 0 to t, integral over omega of phi t squared dx dt. And of course, I get, the extra term coming from the integration by parts in time, which is a remainder term from 0 to capital T. Now, if you want, you can write it that way. You can say that the integral from 0 to t, integral over omega of phi t squared minus gradient phi squared is simply equal to the integral over omega of phi t phi, say, dx from 0 to capital T. This is only the same computation written in a different manner. What I'm saying here is that the difference between the kinetic energy accumulated everywhere in the domain omega during a time interval 0 capital T is equal to the energy accumulated on the potential component during the whole time interval as well, up to some, say, term, which is the crossing of phi t phi. So note that this is important, that from a PD perspective, this term is compact, right? what does it mean that this term is compact? Well, it means that, so you see, if I am working with the solutions of the wave equation, typically phi t is in L2, but phi is in H1, right? In the Sobolev space H1 of functions with gradient in L2, which is compactly embedded in L2. So if you give me a bounded sequence of solutions, I will extract weak limits here and weak limits here. And as you know, when you are taking, nonlinear functions of weakly converging sequences, normally you cannot pass to the limit, right? But here you can, right? Why? Because you see, while phi t converges weakly, the fact that the compactness of the embedding of H1 into L2 will allow you to pass here to the limit in a strong manner, right? And recall that, in an infinite dimensional functional space, right, most cases, a compact set or a compact map is a map that can be approximated by finite rank maps, right? So this really means that although we are in a PV setting, the impact of this remainder term will be very, very, very mild, okay? We will not use that much, but this is something you can take into account. Good. Now, how do I combine this equipartition of energy with this identity? You see, in this identity, there is a common term, which is 1/2, right? So back to the observability inequality. Back to the boundary observability inequality. There is a common term in both, is 1/2 the integral of 0 t integral over omega of phi t squared plus gradient phi squared dx dt, right? So what I did was, from here, I took 1/2, right? So it will remain d minus 1/2. And from here, right, I also take 1/2. So it will remain, right, precisely the same quantity, 1 minus d/2. But here with the minus sign or the plus sign, and here with the minus sign. So what you see that when I extract, the energy, what I get as reminder term is d minus 1/2 of the difference of the two energies, right? And we have seen that, the fact that you move from a plus to a minus, this changes dramatically the situation, because this term, being simply the gap between kinetic and potential, has, the tendency to be very small. This is what we have seen in the harmonic oscillator, where we have seen that although at every time instant, the difference between potential and kinetic energy will be large, when you integrate, for instance, on this arc, right, on this full arc, the energy vanishes, the difference vanishes. So this has the tendency to be very small. Okay, good. Now, what is the price we paid when we did that? Well, I generated, of course, because of this, d minus 1/2 times this term. But recall that we also had another reminder term that was coming from here, right? So then I have, two reminder terms that can be written in the form, right? The two reminder terms are just the integral over omega is always a phi t. In the first one was x gradient phi. Now is going to be d minus 1/2 phi dx integrated, sorry, not integral, just the gap of the two terms between 0 and t, right? Right, and then this goes away, right? and then this goes away. So I repeat, if I come back here, right, I split this d over 2 and this d over 2 into 1, 2, and then the remainder. The remainder is just this difference, right? But this difference, I have replaced it by, you know, the corresponding term here that becomes just a gap between the two values at t equals 0 and t equal capital T that I accumulate with this. And therefore, the identity reads simply this quantity plus this remainder less than the right-hand side that we know is less than capital R over 2, where capital R is simply the size or the diameter, the radius of the largest ball containing omega. Good. And now what is this? We say, oh, but this is just, you know, the integral from 0 to capital T of the energy. But the energy of the solutions is constant. So this is simply T times the initial energy. So you see that we almost got it, right? So we got that, you know, T times the initial energy plus remainder term that is still there, a remainder term that is still there, is smaller than the boundary observation. So it's almost done, but this term is still here. So what do I do with it? Of course, it will be great if this term will have some sign so that I could guarantee, oh, you know, this term is negative, therefore, you know, the inequality is always true. But actually, I don't expect the inequality to be always true. What we have seen yesterday is because of the finite velocity of propagation, typically, in order to get at the energy is bounded by the normal derivative of the boundary. This is what we were discussing earlier this morning, right? When discussing inverse problems, right? If you want to solve these inverse problems in which you are trying to observe what is inside out of boundary measurements, you will need a travel time, you will need a waiting time, you will need time windows that are long enough so that, you know, rays can really cross the domain and give you complete information. So here, I don't really expect the inequality to be true for any time. On the other hand, the structure here doesn't indicate that there will be any sign. I am multiplying three different quantities, phi t gradient phi phi, no hope. Then the only thing I can do is to say, well, now what I do, I will take an upper bound, right? And you can be a little bit more careful about this upper bound, optimizing a little bit, you know, the Cauchy-Schwarz inequality. But basically what I can say is that there is some constant m, so that this quantity is less than m times the energy is 0 and the energy at time t. Why? Well, because simply at any time, if you ask me to give you an estimate, right, of this term, right, at any time, I will apply Cauchy-Schwarz and say that this is less than the L2 norm omega times the L2 norm, right? Omega, sorry, there is no square in Cauchy-Schwarz, okay, like this. Fine. And well, so here, this is very clean. This is just the L2 norm of phi t. Here, something I have more complicated with an x. Oh, but I know that x is bounded by capital R, right? then d is the dimension is also given. Definitely all these by the triangle inequality will be bounded by the norm of the gradient phi in L2 and the norm of phi in L2. But I also have the Poincare inequality, right? That will tell me that, this is less than the norm of gradient phi in L2. Eventually, I will end up getting something like, for a large constant, I will get this. Right? I insist, this is just taking the bound on x through the radius capital R, using the fact that the dimension d is given. This will contribute with a constant term, plus the Poincare inequality, I get this. And this, is, of course, smaller than phi t squared plus the gradient phi squared. And this is precisely m times E of t. So you see, this cross term that I get as reminder in this identity is always, smaller than the energy with the same m, whatever the time is. In particular, because here I am, I have this reminder term from 0 to capital T, I have two i's, the same quantity, because you see, this energy is constant in time. So then it's done. Then we are done. Right? We are very happy that we are done because we got that T times the initial energy minus 2m times the initial energy is less than r over 2, the integral from 0 to t of the normal derivative phi squared, d sigma dt. So m depends on omega and the dimension, and t is arbitrary, right? Well, are we really done? So my goal was to estimate the energy out of the energy concentrated on the boundary, the total energy out of the energy concentrated on the boundary. But here I see a competition, right? I see a t term and I see, another term with a negative sign. So what can I do in that case? Do you have any suggestion? What could I do? Yeah, make T big, large. Thank you, Ma. Indeed, then this means that if T is larger than E, M, that is a constant depending on time, on the domain, then the energy is less than R over 2, 4M, 4M, T greater than 2M, then this will be 4m, the integral over the boundary of the normal derivative of phi. Okay, and we are done. And this is the inequality we wanted. So we have proved that, as a corollary, right? Corollary, if time positive is large enough, depending, with t equal t omega, depending on the geometry of omega, the wave equation is boundary observable and by duality boundary controllable as well. Okay, so the rest of the discussion was done yesterday, right? So we said, well, I follow the formalism of the finite dimensional context. I know that the controllability can be reduced to observability because I can simply build a functional that is coercive on the adjoint whose minimizer gives me the control. I can even apply a gradient descent algorithm in order to minimize this functional and make all these numerically effective. And then the problem is reduced to building the observability inequality, something that we did here by multiplier techniques, right? And as we said, so, you know, the remark about time, I mean, there is an important remark to be done, right? Remark about the time of control. Yeah. So the first remark is that the fact that T positive needs to be large, right, is new with respect to the finite dimensional system, to the finite dimensional dynamical system control theory, right? Why? Because, you know, in finite dimensional control AB, I could check just Kalman, and if Kalman were true, then the time, you know, of control could be arbitrary. The size of the control could be, you know, larger or smaller depending on the time horizon, right? So then the drawing was, okay, you give me, you know, the time window, right? And then I know that the cost of controls, right? So this will be the cost of control, right? Will be CT, right? But this is the case in the finite dimensional theory, right? In the sense that I could take the time interval as short as I wish, and then I could make it, you know, the cost either very large or very long, depending on how long I have in order to divide the task. But in the infinite dimensional case, something that is radically new, right, is that, you know, there is a minimum control time, right, for wave equations, after which, you know, on which the cost of control will blow up, and after which nothing could be done, right? And this is precisely related to the geometric discussion we had, right, about the need that, you know, the action of the boundary gets everywhere into the domain. So there is a waiting time. So there is a waiting time phenomenon for the system to be controlled. Okay. So the first observation is that, well, this is something we did and spontaneously arose in the proof because there were these reminder terms we needed to estimate. So the first time you see, well, this is new. I didn't know this from the finite dimensional theory. This kind of picture on the behavior, on the dependence of the cost of control, right? As a function of the, you know, of the time horizon, right? So, and of course, I remind you that the cost of control, right? So the CT cost of control, independent of whether you are in finite or infinite dimension, is just, you know, what is the constant, right? That you will get as norm of the control depending on the initial data. So here we know that this will be in the dual of the energy space, and this will be in L2 of the boundary, right? In each example, you will have the corresponding topology, but the cost of control is always defined in the same manner. It's just the constant, right, that tells you how big is the control depending on the amplitude of the initial data you have to control. It's a linear map. It's just the norm of this linear map, you know. So it's the norm of the linear map that out of initial data gives you control. Okay, so it's a very natural way of analyzing whether a system is controllable or not, right? It's like if you tell me, can you drive from Changchun to Beijing? Then of course you can, there is a highway, right? But now there is a cost of control. It would take you, we will see later, maybe 9 hours driving, right? So this is the cost. The cost is 9 hours in that case. Very good. So the first remark is, oh, you know, this is totally new for us. We didn't know that such phenomena could occur. In the finite dimensional case, this waiting time phenomena, right, is really an infinite dimensional. So this is a feature of infinite dimensional control systems. That doesn't occur in finite D, right? And the second remark is that this is not something technical. It's not that, you know, we get this. It's not that we get this kind of minimal time. So this is the, you know, minimal control time. It's not that we get this minimal control time because we, you know, we were very rough on our, say, energy estimates and so on, and integration by parts. It's like it's, you know, intrinsic to the process we are considering. Why? So this is intrinsic to the wave phenomena under consideration, and is related to the finite velocity of propagation, right? Given that, you know, there is a finite velocity of propagation, you will never be able to get control in time too short. You need the, you know, the time that, you know, the action on the boundary penetrates and covers the full domain. Okay, so maybe just a last remark on this is on this point, right? Let me see, where did I say it? Here, right? Here, right? Here, maybe I could have done it better, right? Do you have any suggestion of how could I improve this estimate? So here I did it brute force, right? I said, I mean, the absolute value of this quantity, I put the absolute value inside, and then I say that the norm of x mu, the absolute value, Cotier Schwarz, is always less than r. So this is good, right? It's you know, it's correct. But do you think that I could have done it a bit better, maybe? Do you have any suggestion of how could I make this estimate a bit more careful? Yeah, so we can discuss, you know, the relation of the shape of the boundary and the sign, right, of x nu, right? So let me just make a comment on control on part of the boundary. And it's actually quite simple, right? It's simply, you know, to make more colorful upper bounds on the boundary term. So what did we have? We had something like this on the boundary. And then I was tough. I said, you know, this absolute value of x times nu is less than capital R. I put capital R everywhere and that's it. Well, but of course, right? I could split this into, you know, the set where the multiplier is positive and the set where the multiplier is negative, right? Denoted by, you know, the corresponding signs, right? So I say that, you know, the boundary of omega is split into two parts, right? So here I am splitting the boundary of omega into two parts, omega plus and omega minus, right? Omega plus being the subset of the boundary where x mu is positive, and omega minus is the subset of the boundary where x mu is negative, right? This can always be done. I mean, you give me any function and I can always distinguish, you know, the measurable set of the support where the function is positive almost everywhere, and the, you know, and the measurable set where the function is negative almost everywhere, which will be separated by, you know, the nodal line where the function vanishes. I mean, I can always do this. And then because of that, of course, I can then immediately guarantee that, you know, this term being negative, and this term is negative by definition because this is the set where the multiplier is negative and this is a square which is always positive, then, right, then, you know, this term, the bound on this term will be always achieved with the same constant R, but only localized on the, you know, this component of the boundary. So now, how can I check this? For instance, let me see some examples, right? So I take, for example, omega to be the disk, right? Right. So if I place the disk omega here, right? This is omega, and this is 0, right? What is the set? Can you please tell me what is the set of x on the boundary of the disk so that x times nu is positive? You see, in order to check when this sign is positive, you have to take any point on the boundary, right? And draw the exterior normal vector, and then, you know, compute the scalar product, right, with the vector x, right? So this is x, right? So this is the vector x joining 0 with the point on the boundary where you stand, x, and this is mu x. This is the exterior normal vector. You take another point here, right? And you do the same, normal mu x, and then here you have the vector x, right? And then you have vectors, points like in here, right? Where, you know, the x vector is pointing in that direction, and then mu in that direction, and there are points here clearly, right, on the opposite side, right, like in here, where, you know, the normal and the diameter, right, and the radius and the normal are pointing in opposite directions. So when is x times nu greater than 0? Well, it's simply on those points where the angle of orientation of the two vectors is less than, say, pi, right? Then you will see, or pi over 2. Then you see that, you know, in the boundary of the domain, I don't know which color I should use, so maybe this, right? Can be split into two parts in which, you know, this is the d omega minus, right? And this is the d omega plus. So essentially, right, given a disk, right, depending on how far it is from the origin, right, you will always be able to control, right, the wave equation with a, you know, part of the boundary, right, just bigger than half, you know, the boundary of the disk. Okay, so then the remark is, well, when I do this geometric analysis, I see something very simple. If the domain is a disk, and you tell me where is the part of the boundary where the control or the observation needs to be active to observe or control the system, I tell you it's just the half of the boundary, a little bit more than half of the boundary. That's the conclusion. And then the other remark is that this is sharp, right? And this is sharp because if someone comes to you telling you, oh, you see, I do better than you. I take, you know, the disk and I place the observation in this small piece and I can observe the wave equation. Then you will tell him, not really, because there is a diameter, there is an array of geometric optics. There are several actually, right? There are several rays. All these diameters that escape, you know, the red arc, right, escape to the observation. So you see that, of course, all these diameters should cross at the same point. It's not very nice that what I draw, right? So if I take this circle, right, then, you know, the diameters should cross at the center. Okay, so I think you understand me, right? Okay, so then you cannot do it, right? Because the observation subset of the boundary has to intersect all the diameters. Very good. So now this was on the circle. Maybe the second example that we can do, these are the simplest, is the square domain, right? If you place the point here, what happens then in the square domain? Well, typically you will get control on these three parts, right? So this is the control set, right? Three sides. Do you think I could do better? Do you think I could control the wave equation with control only in two sides of the domain of the square? So here, when I place the center of the origin here, I clearly get three sides, right? Because, you know, the rays will be, you know, here I am simply decomposing the boundary on the domain of the region where the rays are incoming and the regions where the rays are outgoing, right? This is the distinction, you know? In order to determine whether x mu is positive or negative, you simply draw the ray joining 0 and x, and you check whether it's coming in or coming out, right? Good. So here is the same. When I launch rays from here, of course, in this side, I see how the rays are coming in. But of course, on this side, and on this side, I see how the rays are coming out. This is why I get three sides. So Ma says that I cannot get two sides. Are you sure, Ma? What happens if I do this? So I take, right, for instance, here, and I just place the center of gravity here, the 0 set here. So then in this case, you see that the, you know, that the zone where x mu is really positive, right, it will be only constituted by two sides. So we can also control the wave equation by acting on two adjacent sides. So please understand it correctly. I'm not saying that you can control the wave equation controlling here and controlling here, right? Because these are indeed two sides, but these are two non-adjacent sides, right? They are not connected. They don't have any point, any corner in common. And these two sides will never be the exit region of, you know, the rays out of any focus, right? So could you please give another argument to show that actually in this case the wave equation cannot be controllable? If we think in terms of the propagation of rays inside, what do you see when you look to this picture? So there is indeed a dangerous situation, right, where the ray will be propagating forever along this vertical ray, right? The energy will be propagating along this vertical ray, and this will never be observed, right? So this is a non-observable or controllable configuration. So we see that in some sense, what this is telling us, listen, given any domain omega, right, the pieces, the arcs of the boundary on which you need to, you know, focus the energy in order to get observability or concentrate the control in order to get controllability depend on the domain omega and are quite large, right? You know, here, for instance, it's more than half. Here it can be just half, but not less. But not each half will work, right? Okay. And sometimes, right, even taking more than half will not suffice, right? Because you could also do this and say, okay, I'm going to control all here, right? Here, 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 and even here. But if you forget, you know, that there was also a vertical ray that could be trapped there, and if you miss to control here and there, right, you will not get the controllability. So getting control or not is not just a matter of size, of how much, you know, of the perimeter of the, right? So this is a non-controllable configuration. Although the control acts in a nearly 100% subset of the boundary, right? It's not a matter of how much of the perimeter you get, is also a strategic placement in which, of course, you can never miss any of the rays that are crossing, you know, the domain omega. The same will happen if you were dealing with an inverse problem, right? So, you know, similar as in inverse problems, right? Right. So if you are checking, you know, trying to get some image of the brain, and you just take one ray and then another ray and then another ray, of course, there can be anything in here, right? And you will never be able to see it, right? You will never be able to see this because your rays are not passing by, right? This is why you need a much more, this is what you do with the radon transform. You need a much more exhaustive covering on the plane to make sure that all the obstacles that could be inside, that will be the defect you are looking to, could be a defect on a material, or it could be some fracture on a bone, you will need them, right? many more rays in order to see these defects inside. Okay, and maybe I have another third example, and the last one I would like to discuss is domains with faults, right? Right. So you recall we said, well, we are ready to accept that if you give me such a domain, but this domain has some defects, right? Some faults here. There could be a ray trapped so that, you know, the control on the exterior here the control on the exterior boundary does not suffice because of the ray trapped within the two obstacles. Right? So this is something we understood from the perspective of the ray analysis, the velocity of propagation of rays and the geometry of the propagation of rays. But does the multiplier technique see this? Let's check what happens when you do multipliers. So let me place the center of gravity here, right? The 0 here. So I launch. And then what the multiplier technique will tell me, well, Enrique, you need to control all around here where the rays are exited, right? So I will need to control all around here. But I have also to check, you know, how these rays are interacting with these obstacles, because these obstacles are also part of the, you know, of the geometry, right? Of the boundary, are part of the boundary of the domain omega. So we said that I need always to control where the rays are exiting, right? And where are they exiting here? So these rays are exiting the domain when they get into the obstacle, right? When they get into the obstacle. And therefore, you know, I will have also controlling here. And here they will also do it, sorry. They will also do it when the rays exit the domain, which means penetrating into the blue region where, right? Into the blue region, which is the obstacle out of the domain. So the control, right, could be here. And then if you do carefully the computation, you will see that, you know, precisely the fact that when I do the multiplier technique, the multiplier tells me that there is control on the exterior arc of the boundary, but also on a piece of this boundary and a piece of this boundary guarantees that in case there is any trap ray, as in this example, this ray is either on this brown side or in this brown side, depending on whether the center of gravity was here to the left or to the right. But definitely this ray will be observed, right? So, you know, the multiplier identity, right? The multiplier technique leads to arcs of control on the exterior boundary, but also on the obstacles inside, guaranteeing the control of all waves. Okay, just to conclude, a final comment. So we said, what is the consequence in terms of control? we said, not only you can prove an observability inequality like this, right? We said, not only you can prove an observability inequality like this for all t when t is large enough, right? But we could improve it into an observability inequality in which I was just observing on part of the boundary, right? So the same inequality, but observation on part of the boundary. What is the control consequence? Well, you see, there is some rationale on all this, thanks to the duality between, control and observation, right? The least we need to observe, it means also that the least control we need to use to control the system. So what it means is that for the wave equation, on the domain omega, with boundary conditions that are, some active boundary condition on the region of the boundary where the observations are being made, but zero on the complement, right? And then initial conditions y0 and y1, right? I can guarantee that the system is driven to zero, right? So the controllability is guaranteed with controls U with support in d omega plus cross zero t, right? This is the bonus you get out of this. And then if you are interested on computational aspects, you will ask me, and what is the difference? So you said that in order to, so we go back here, we said, oh, in order to compute the control, I needed to minimize a functional, right? I needed to minimize a functional. Where it was? Oh, here it was. It was this functional, right? In which there was a quadratic part that was precisely the key, right? Using the normal derivative of the adjoint to compute the controls. What will be the difference now when I am controlling just on the boundary plus? Well, there is not much difference. Then, it suffices to minimize the functional, right? So I will denote it like Gj d omega plus phi 0t phi 1t, which is 1/2 the integral. And then the only difference with respect to the other functional will be that now the integral, right, will just be, on this piece of the boundary. Right? So that's the only difference. And then I will tell you, okay, now you do your numerics, you replace your wave equation by a convergent numerical scheme for the wave equation. You replace this functional by the corresponding discrete version. You apply a gradient descent iteration and blah, blah, blah. I mean, you have to do that very carefully, of course. But provided you have taken, the arc of the boundary, the subset of the boundary, guaranteeing the observability, this functional is coercive and everything will go through, right? And if someone tells you, well, because this is so simple, so this will give you some, minimizer, right? This will be the minimizer. And the control will then be, the normal derivative of this minimizer, but now localized within the control region, right? And if someone says, oh, but if it is that simple, right? So why don't I, adopt the same point of view, but I make this arc of the boundary to be even smaller than those that, the multiplier technique lists? Because you see, in the multiplier technique, I am always bounded by this kind of geometric constraints. Then you can say, well, you can try to do the same with a subset of the boundary that is very small, for instance, like in here, right? Where, I was missing, like in here, where I was missing the observability inequality. What happens then? Well, be careful, because you see, this functional is not coercive anymore, right? So you don't really know whether there will be a minimizer. And of course, the functional not being coercive, it means that this quadratic form doesn't have a lower bound. And whenever you apply a gradient descent algorithm, right, you will not even know whether you can take a step size rho, which guarantees that this descent algorithm converges. Because you remember, the rho on the steepest descent in the simplest application of the steepest descent, but is the one that really enlightens what's going on. The step size was smaller than, capital M over alpha. What, it was simply the maximum eigenvalue, right, divided by, the reverse, right? It was the minimal eigenvalue, alpha over M, the minimal eigenvalue divided by the maximal eigenvalue. There was lambda 0 and lambda max, right? Lambda mean and lambda max. So, but, when the coercivity of this functional fails, it means that the coercivity constant is 0. It means that lambda 0 is 0. So it means that in order to apply the gradient descent algorithm, you will need to take a step size equal to 0. But of course, if you take a step size equal to 0, the descent algorithm doesn't even start marching, right? It's simply frozen on the initial configuration. So everything breaks down as soon as you break these geometric rules that are needed for the observability and controllability. And of course, if you want to see closer things, more detail, you will need to get into a much more sophisticated micro-local analysis of the billiard. But at this level, you already see how important the geometry is in these wave control processes, right? And to which extent you also see the fact that, in infinite dimensional system, new scenarios arise. In particular, right? There is a waiting time, right, appearing, in the sense that the control can only achieve for t large enough because of the finite velocity of propagation. Okay, so probably those that, just before we go to the break, those that are used to, partial differential equations, another kind of properties of other models of partial differential equations could think, well, but, Enrique, you took the wave equation where there is finite velocity of propagation. But if you take the heat equation, then the velocity of propagation is infinity. And maybe you can expect the control results to hold in any time, right? And this is actually true, right? So you could take now the heat equation process, with control on the boundary, right? And then in that case, you can guarantee that it can be controlled to 0 in any time, right? So the heat equation in some sense behaves like the finite dimensional systems, right? And this is due to the fact that the dissipativity of the Laplacian in the heat equation is so large, right? This generates an analytic semigroup. Actually, when you draw the spectrum of the heat equation on the line you see that, you know, the spectrum is located always, they are all real and going to minus infinity, right? It's simply minus lambda j are the positive eigenvalues of the Laplacian in H10 omega. Okay. So the spectrum is moving to minus infinity so fast that the dissipative effects of this heat equation are so large that eventually, from a control perspective, it behaves like a finite dimensional system in some sense. So then, you know, this is why, you know, the subtle control properties of partial differential equations are not as simple either, right? Because we said, well, I wanted to do Kalman in infinite dimensions. I did not succeed. I analyzed the wave equation. I discovered new phenomena like the waiting time, right? For, you know, for the control of the heat equation, all these geometric features. But when I get into the heat equation, somehow this seems to disappear because the system is dissipative enough so to allow to achieve results that are similar to the finite dimensional case. Yes, this is true, but this is very subtle, right? So for instance, when you take fractional heat equations or heat equations with memory terms, etc., you could be in situations where the system is, you know, is in between parabolic heat equation and hyperbolic wave equation, and very often is not so easy to determine whether the control property holds in any time, you know. So remark here is, remark, right? Careful with hybrid systems combining parabolic and hyperbolic phenomena, right? What do I mean by this? I mean, well, if you have models that are hybrid, take a little bit from wave equation and a little bit from heat equation, whether the model behaves more in a parabolic manner or in a hyperbolic manner, it will depend on how strong each of the two effects is. And this could lead to phenomena like, you know, either requiring time to be large, like in the wave equation, or the system to be controllable in any time, right? So this is an important feature. Simply because, as we have discovered, by looking to the simplest PDE models, wave and heat equation, you see a completely different behavior at a control level. So is there any relation to between the heat and wave equation? There is a very interesting relation. And is that this is also known by people doing semi-group theory, also you know, people dealing with numerical analysis. This has been very much used, you know, in mathematical physics. Is that the heat equation is subordinated to the wave equation. So what I claim is that the heat equation is subordinated to the wave equation. This might look surprising, right? Because when we study partial differential equations, wave equations are on one side, heat equations are like in a different category, right? And actually, you know, the fundamental solution on one and the other, you know, are completely different. So on the wave equation are just propagation of along characteristics. On the heat equation, by the contrary, is the Gaussian, say, convolution. So why do I say that one is subordinated to the other? The remark is the following, and it's a purely, say, not only valid for the heat equation and for the wave equation, but is general to any, say, generator of a semigroup, right? So assume, you know, we want to solve this equation, yt plus ay equals 0 for t positive, and y0 equal to y0, right? So this is a Cauchy problem, right, with y belonging to the space of continuous functions in time with values in some Banach space. So you see, this could be, you know, the heat equation, right? In that case, A is minus the Laplacian, but it could be also, you know, an ODE system, right? In which X is simply Rn, and A is an n by n matrix, right? So what I'm saying is valid both for infinite dimensional systems and finite dimensional systems. This is general to all kind of Cauchy problems, right? The only thing I am using here is that A is linear, right? And time independent. That's the only thing I'm using. I'm not, you know, interested on whether the dimension of the space X is infinite, PDEs, heat equation, or finite, you know, ODEs, right? Ordinary differential equation. And then, so our goal is to compute the solution of this, right? This is a parabolic problem. And assume, you know, is your first course in partial differential equations, or even in ordinary differential equations, and your professor asks you to solve this equation. But the only thing you have learned in class is to solve, rather, models of the form with two time derivatives. Right? With two time derivatives. Right? So now S is a pseudo time. Just a parameter. Okay. So I tell you, well, in my, you know, my professor in, you know, in ordinary differential equations or partial differential equations had a very peculiar perspective to this. He said, I first solve an equation of this form. Well, of course, you know, I call it S. This is a pseudo parameter just to make the distinction with the true T parameter, right? Because, you know, I'm dealing with a heat process. I'm checking how heat propagates in the building where I am living. And then I am interested on the evolution along the real time, because this is the time on which I am living. But in order to make the computation, because my professor did it that way, I moved into a different model, which is second order in time, and I make it evolve according to a pseudo time variable, right? Okay, so then, of course, this is a second order in time equation, then it's time reversible, and I can solve it, for the pseudo time S from minus infinity to plus infinity, because the system is reversible in time. It's not like the heat equation that I can go forward, but is, you know, the Cauchy problem is imposed in the backward sense. And because I was asked to solve the, you know, the heat equation with this initial datum, this is the initial datum I place here as well. But I know that this wave equation has to be solved. This is a wave-like equation, second order in time, right? So this is a heat-like. This heat-like, right? But this is wave-like. Because, you know, this is a second order in time, in pseudo-time equation, I need also an initial velocity. I take it to be 0, right? Because in this way, you know, the solution of the wave equation, right, it will be, you know, symmetric with respect to this pseudo time variable S, right? Is the fact that the velocity here is equal to 0. Okay, good. Then the Canai transform says, okay, so if you know how to solve this equation, then you also know how to solve this equation. Why? Because my claim is the following. I claim that the fantastic formula is that y at time t is just the integral from minus infinity to plus infinity of z of s k s t s ds, where k s t is simply 4 pi t minus 1 over 2, sorry, 4 pi t, yeah, exponential of minus s squared over 4t, which is just the Gaussian, right? Solving the heat equation in 1D with initial datum, the Dirac delta at s equals 0, right? So what does the Kanai transform say? And this is the key result I wanted to show you, is that if you know the solution of the wave equation, then you can immediately deduce the solution of the heat equation. How do I do it? Solve according to this formula, solve the wave equation for minus infinity to plus infinity, right? And once you have done that, integrate all these values, all these layers for every s, for every pseudo time s, you will have a slice of the solution of the wave equation. You put them all in the same, wok, and then you shake it, you mix it according to the heat kernel. This new object, of course, because I am integrating with respect to x, will only depend on t. And this will be the solution of the heat equation we were looking at, right? This one. This is why I say that the heat equation is subordinated to the wave equation, because if you, solve the wave problem, out of the wave problem, by making some kind of mixing, averaging, or projection, through this mixing operator, you can compute the solution of the heat equation. And this is why also you can observe that there is infinite velocity of propagation on the heat equation. Because here, there is finite velocity of propagation. Waves travel with velocity 1, and then ping-ponging on the boundary and so on. But here, because you have integrated this process from minus infinity to plus infinity, all these characteristic rays have the opportunity to travel infinite distance from minus infinity to plus infinity. And this is why here in a time instant, you see all this averaging and you see a completely global process, which is the one that the heat equation, shows, okay? So I will conclude the proof of this Kanai transform, and then I will tell you about the Turnpike principle, okay? So maybe for those that prefer to remain active during the break, please try to solve this exercise. Show that this function y as a function of t defined that way solves the heat equation, okay? Yeah, so the first thing we have to discuss is the convergence of this integral, right? Is this integral convergent? So realize, please, that z of s, although it's written, maybe it should not draw it that way. It should have been something with, say, more like an oscillatory behavior, because, typically, this system will conserve energy. So the amplitude of z, in particular when, when A is a self-adjoint operator, the size of z, the norm of z, of the trajectory will be the same for all s. So it will be kind of an oscillatory pattern in which, z of s will not decay as s goes to infinity. So you have to be careful about the integrability of this function. But you say, this is multiplied by k. So at any t, k, which depends on s, is this Gaussian function, right? So then, even though z does not decay, k, does decay for any t as a function of s. And therefore, the exponential decay of this K kernel is the one that makes this integral to be well defined, right? So this is a Bochner integral that is well defined. That's the first remark. Now the second remark, what do I need to check? I need to verify whether Y fulfills the heat equation with this initial datum. And this is true, because when you take Y at t equals 0, right? This is by construction the integral from minus infinity to plus infinity of z of s k s 0 ds. But we know that the initial datum for the heat kernel is just the Dirac delta at the center s equals 0. So because this is precisely the Dirac delta s equals 0 applied to z of s, right? Then this will give me z of 0, and I was careful enough to take the initial datum for z to be y0, the initial datum for the Cauchy problem of the first order heat-like system. So this is indeed y0. So you see, out of the two conditions that I need to verify to show that this, heat solution obtained out of the transmutation, say, subordination principle of this Kanai formula fulfills this heat equation, I have already the initial datum. Let me now check, the time derivative. What is the time derivative of y? Well, it's the time derivative of this integral of zs kst ds. But the time derivative and the integrability and the integration with respect to s, they commute, right? And all this can be justified because k is extremely smooth. The decays exponentially and is very smooth. So then, when you take the time integral here, what you will get is that the integral of the time derivative of what is inside. But the time derivative of this, you see the first term is independent of s, and then you will have the time derivative of k. But the time derivative of k, because k is defined as the classical heat kernel, in which one time derivative is equal to two s derivatives, it will be equal to, right, two s derivatives of k with respect to s. And now you will integrate by parts twice, right, and pass these two s derivatives into z, right? Because we integrate by parts twice, we get minus minus, but this is eventually a plus. And I will get CSSS KST ds, right? In this integration by parts is completely justified. In particular, I don't have any difficulty with the possible contributions at minus and at plus infinity because the kernel K is decaying exponentially, so no boundary terms. And now I know that ZSS is equal, according to the computation here, to minus AZ. So this is, minus of AZ KST ds. And this is minus A applied to the integral of ZS KST. So you see that here I am using the linearity. Here I am using, right? So here at this key point of the proof, I'm using the linearity and T independence of A, right? And you see that this is precisely minus A times what? Well, it's minus A times this integral, but this integral is by definition, right, the y of t, right? So the conclusion is that it is true that dy dt is plus AA, AEY, is equal to 0 as well. So this is the canine transform. This shows the subordination of the wave equation, the heat equation to the wave equation. As I said, this can be used in different contexts, in semigroup theory, numerical analysis, in mathematical physics, right, for solving inverse problems as well. Why? Because you see, in the heat equation, in particular, it's much harder to see the geometry of the domain because everything is mixed up, right? So very often when one is solving inverse problems, although the wave equation is more complicated, right, and is second order in time, one sees much better because one can follow track solutions along ray, and then, we know that the ray will follow the geodesics. It will be adapted to the topography of the medium under consideration, to the geometry of the domain, the manifold, etc. And it will also take into account the travel time. So, this kind of transformation is, of universal application in many, many topics in which the link between the heat equation and the wave equation, right, is of interest. And it can also be applied for control. I will not get into the details here, but one can, for instance, out of the control of the wave equation, right? This transform can be also used in the control context to derive control properties of the heat equation out of those of the wave equation. Okay, good. So I will close then this chapter now. I will clean out these notes and send them to Professor Kai maybe tomorrow or early next week, so that they can be made available also for the attendees of the course. I would like to move now on and discuss the Turnpike property. This is another important paradigm in control theory, also in connection with machine learning and supervised learning. But before I do that, so maybe if there is time for a quick question. Do you have any comment on this part? Okay. So if not, let me now move on to the Turnpike property. So as you see, now I will discuss two topics that in principle are completely independent, but as we will see, as it often occurs, there are some interesting connections that I will try to highlight. Okay, very good. Okay, so first, this is something we have already seen. From a control perspective, the topic is very classical. It was already, anticipated. The importance of the topic was anticipated by Norbert Wiener, who, talk about, the duality between communication and control, right? In order to discuss this topic, we started by the simplest paradigmatic problem of controlling a linear finite-dimensional system. We see here the picture of Professor Rudolf Kalman that passed away 5 years ago. And well, in particular, in the context of open-loop control, he was one of those pioneers clarifying that, controlling a linear system is just about checking this run condition, right? And that once you are able to do it, then the control of the system can be guaranteed in any time, right? Then we have seen that this can be proved thanks to, you know, the variation of constant formula and the Cayley-Hamilton, right? And there is this important remark here, right? That, you know, the fact that we can control systems is because when we combine, do and undo, right, the same operations in a switching pattern, often, right, we recover properties that are not so obvious a priori. And this is why we have shown, you take, for instance, a four-dimensional car because there are two dimensions for the center of gravity, one dimension for the, you know, for the orientation of the main axis, and the last dimension, the fourth dimension, for the orientation of the angle of the wheels with respect to the main axis. This is a four-dimensional system that you can control, right, just by accelerating. So a force oriented in the direction of the main axis and the rotation of the wheel, so two controls and four dimensions, simply because we know that if we move forward, left, backward, right, we don't get to the same configuration, but rather we are doing the manipulation that, you know, allows me to move the car, keeping the center of gravity, right, and reorienting the main axis. Something that in principle, if you look to how you can operate a car, you could not do, because either you are standing at the same point and then you rotate the wheels, but this produces no motion on the car because there is no acceleration, or you accelerate and then you are moving the center of gravity. Despite of this combination of forward, left, backward, right, or if you want, backward, right, forward, left, allows you to produce this kind of rotations on the car, right? So this is something that we know, that we learn to do, you know, in the auto school, right? In the school for, you know, getting the driving permit. But in fact, we could have said, well, no, I don't need the driving permit because I know, you know, the Kalman rank condition. We could also do this, right? And say, well, no, I don't take the classes, right? I get the permit just because I know the Kalman rank condition. You can try. And then we have discussed, you know, the main observation, the main ideas introduced by Lyons in this science review paper in '88, where he said, listen, if you want to move into partial differential equations, this kind of Kalman rank condition is not sufficient, but you can analyze things through the duality principle, in which everything is reduced. So here it should be a P. Everything is reduced to the observability inequality. And in the last few days, we have seen, yesterday and today, we have seen that the observability of the wave equation can be proved using multiplier techniques. It's not that difficult, but it's tricky because the geometry of waves of the domains appear. The time of control needs to be large enough, right? Something that you didn't expect out of the finite-dimensional theory. And also that we can handle heat equations because the heat equation is subordinated to the wave equation through the Kanai transform or the, you know, the transmutation transformation, right? Other than this, out of this theory, we know that the controls can be computed as B star P hat being the minimizer of this functional. And because the observability inequality, this functional has a minimizer because this is coercive, the quadratic part is coercive, and this can be made algorithmic through adjoint methodologies. Okay, good. So now, what about the Turnpike? So I was introduced to this topic in some sense, right? At that time, we didn't know of, you know, this concept of Turnpike. I will mention now what it is. I was introduced to this topic by Francisco Palacio, who was a former PhD student in our team in Autónoma de Madrid, maybe 15 years back or so. Today, he's working in Boeing in California. And his PhD thesis was about aeronautic optimal shape design, right? there are many very interesting, say, research directions oriented to, you know, the optimal shape design of aircrafts, right? And one of them is related with sonic boom minimization. There is a very nice survey article that I recommend you to have a look by Juan Alonso and Michael Colono in the Annual Reviews of Fluid Dynamics 9 years back, where they describe some of the challenges appear in the, you know, in the design and construction of the new generation of supersonic aircrafts. As you know, one of the difficulties of supersonic aircrafts, of course, they are much faster, but because of the fact that the flight goes beyond the barrier of sound, you know, when the aircraft reaches this critical, say, sound speed, it generates a sonic boom. You know, it's a boom, it's an explosion, and this explosion, which is a, you know, a shock wave, acoustic wave, it propagates down to the floor, right? You know, to the earth, right? This is maybe 10 or 15 kilometers high. It takes some time to get to the ground, but when it takes to the ground, is not admissible when you are, you know, traveling on populated areas, right? So then there are two possibilities. Either, right, in some sense, you make this sonic bound be so that when it gets to the ground, the amplitude is sufficiently mild so that it's compatible with, you know, flying over populated areas. So, you know, is below the level of noise that authorities, governments will allow for populated areas, or the second possibility is that you can fly supersonic only when you are not flying over populated areas. But then, of course, you know, the benefit of being supersonic diminishes because it means you cannot be supersonic all the time, right? So these are like these fast trains that can only be fast on some small arcs of the railway, you know, path. Then you don't really benefit of the fast, you know, velocity of transport, right? Because you have to be slowing down again and again and again when crossing different areas. So here is the same. Now, you see that because the flight of this airplane occurs at a very high altitude, you know, even when the shock is generated, right, it takes a while before it gets to the ground, right? So this means that the time horizon in this problem will be long. On the other hand, you know, what is the challenge from the perspective of the optimal design in aeronautic industry? The challenge, as I said, is to make, you know, this sonic boom to have the amplitude to be small enough and the signature, you know, the shape of this sonic boom to be appropriate so that, right, when it gets to the ground, is acceptable, right? Then the question is, how do you shape the aircraft so that, you know, whenever this sonic boom is generated, when getting to the ground, after a very long time, you know, the signal is admissible. So this is like a control problem in which you are controlling the initial datum or the shape of your domain so that when time, you know, you get to the final time, which is when the sonic boom reaches the ground, the signal is small enough. So this is a control problem in a long time horizon, right? And there are many control problems in long time horizon, right? So for instance, when you, I did this morning, I did Google, right? And I said, okay, I want to drive from Changchun to Beijing, right? You see it is written in Spanish with accents and everything, okay? This is Changchun and this is Beijing. So when you wanna drive from Changchun to Beijing, you know, Google tells you there is one path which is optimal, right? Is 9 hours 35 minutes, and there is another one which is suboptimal, is shorter, right? Is shorter, I don't know, maybe it's nicer also, maybe it goes along the countryside, I don't know. But it takes you, you know, like 40 minutes more, right? Well, actually, it's not shorter, it's five kilometers longer. So they are almost identical, right, in length. There is just a gap of, you know, 5 kilometers out of nearly 1,000. But, you know, this one is faster, it's 9 hours, 35 minutes. And you see, when I asked to Google to tell me what is the time to go from Changchun to Beijing, right? It didn't actually ask me whether I am departing, you know, in Changchun from Jilin University and whether in Beijing I am going to Tiananmen Square or to the building of the Academy of Science. No, no, they didn't ask me. I said Changchun, Beijing, and I got this path. So what does it mean? Well, it means several things, right? Probably the first thing it means is that, well, the map, you know, the road here is simply linking, you know, the center, the city center, some geometric city center in Changchun with a geometric city center in Beijing, which is maybe in Tiananmen, right? Okay, fine. Maybe this is the reason. But you see, I don't get all the details of the many streets and roads I have to take, you know, out of Changchun and into Beijing. Certainly, if I will, you know, zoom in, right, this path and look closer to the city center of Changchun and Beijing, I will see a lot of, you know, highways crossing, roads, zigzag of the path I have to do in order to, you know, get into the complexity of the urban areas, right? Or get out of it. Okay. But in fact, it was thinking on these kind of situations that, you know, von Neumann designed the principle of Turnpike, right? There was later Paul Samuelson, who got the Nobel Prize in economics, who further developed this, in particular on his book with Robert Slow, right? The principle is the following, as explained here. It says the following: when you are, you know, controlling, right, from one point to another that are very, very, very distant, essentially, right, the optimal path is always the same, right? So what this is telling me is that, well, depending on where you depart, right, in Changchun, of course, you have to zigzag differently to get to the highway, right? So it's not the same if you depart from one place or the other. The initial arc of the control process will change. The same in the end, when you are going to Beijing, it's not the same going to the university, right? Or going to the hotel, right? There will be final arcs that will also differ. But the essential of the trip, 99% of the trip will hold along the same path, right? And this is precisely what this principle says, right? When you are traveling from one point to another, right, which are very distant away, right, the control is realized in three regimes. There is an initial arc that depends very much on where you are starting from. Then most of the time, there is a dominant arc along which you always, independent of what is the starting point and the destination point, you will follow the same path. And it's only when you are getting close to the target that you will quit this highway, right, this Turnpike, and then, you know, you will again produce a small arc, right, which is aimed to drive you to the destination you have, right? So two different travelers from Changchun to Beijing will essentially, you know, follow the same track, the same path, that will only be distinguished by the initial action and the last phase, just to make sure the trajectory is adapted to the point of departure and the point of destination, okay? And this is the representation, right? So there is, you know, I start from y0. I want to get here to yt, right? And then what the Turnpike principle says, well, there is a highway, right, that I have to join. So the best possible option, right, to go from y0 to yt is that I go straight to the highway, and then I follow the highway, and then I get out. If for any reason you change the point of departure and the point of destination here, right, then you will slightly modify your trajectory, right, because you will do something like this, and then you will continue the same path, and you will exit to go there. But you see again that during most of the time interval, independent of what is the initial point and the final point, most of the time, the trajectory will be the same. This is the Turnpike principle, okay? And Turnpike in English is the, you know, is the name for highways, right? Okay, so, well, this is what the theory says. But this is not what we have seen. Actually, we have seen that when we control the wave equation, the controls will look that way. Why? You recall, right? The control of the wave equation was just the normal derivative of the adjoint, right? But when you are considering the wave equation on a domain, right, the solutions are oscillating. So the normal derivative also, right, will be an oscillatory function. And this is actually what you see. I mean, if you do numerical simulations for the control of the wave equation in one space dimension, you compute the boundary control, and this is what you will get. And actually, we are not so surprised, because we know that the Fourier representation of solutions of the wave equation exhibits always an oscillatory pattern. Actually, even if you think in terms of the propagation of characteristics, right, this is how the solutions of the wave equation look. And therefore, the controls have to be on and off. They have to be of an oscillatory nature, because, as you know, the action of the boundary control is precisely to apply an anti-wave whenever the wave is incoming and reaching the control region. There were also numerical simulations done by, you know, by Lyons and Glovansky and Lyons in the 80s. They have some nice articles, even a book on this. And for the heat equation, they found this kind of structures. They were a bit surprised, right? They said, well, I mean, if the heat equation is going down, right? If the heat equation is dissipative, why the control of the heat equation as time evolves, rather than going also, you know, ongoing some kind of dissipative or relaxation, say, pattern, the control of the heat equation seems to be very active at the end, while the solution is already going down. So why, you know, the control of the heat equation doesn't go down, but rather when getting to the end, is acting more and more and more, right? This is like a bicycle race, right? Where, you know, the runners, you know, run, you know, pedal for hours, and it's in the last, say, 100 meters where, you know, the final race occurs, and then they have to, you know, maximize the effort, right? So why this happens, and how is this related to the Turnpike principle that von Neumann and Samuelson anticipated? In particular, you see, when you go back to the wave equation, the oscillatory pattern of the solution will always occur. So this is independent. This observation is independent of the time horizon. Of course, I know that the amplitude will depend on the time horizon. When the time horizon is shorter and you are getting close to the minimal control time, the amplitude will be large. When you take time horizons very long, the amplitude of the control will be small. But the fact that the controls will be of an oscillatory nature is intimately related to the fact that the controls are given by the adjoint heat equation, and the adjoint heat equation oscillates forever. So I don't see the Turnpike principle here. I see that I am ping-ponging, zigzagging all the time. I don't see that I'm getting into a highway where the control is kept, more or less to be constant. This is what you do on the highway, right? You have to work hard to get from home to the highway. Once you are on the highway, you set up 120 kilometers per hour and you go a straight line. Right? You could let the autonomous car to guide you, right? And you could be doing something else once you are in the Turnpike regime. Not initially, neither in the end, where you have to be very active to avoid all the obstacles, be careful to pedestrians crossing, to the red lights, and all the bifurcations of the streets near the downtown. So I don't see the Turnpike here. So then I said, okay, I look to the heat equation, and I don't see the Turnpike here. So I see that there is a lot too much, work ongoing, and I don't see a flat regime. It's like, we start very slowly, and then the process of controlling the heat equation accelerates. Why is that? Well, the reason is precisely what we have shown, is that for the wave equation, the control is given by the adjoint of the wave equation. And for the heat equation, using the transmutation principle, you will see that the control, right, is given by the adjoint of the heat equation. And how do these solutions behave? Well, you see, it's very simple. On the wave equation, this is a purely oscillatory pattern. And on the heat equation, how is this solution behaving? Well, this is like the Cauchy problem for the heat equation, but backwards in the sense of time, meaning that if traditionally the solutions of the heat equation are going down when time increases, in the present case here, the solutions of the heat equation will go down as time, goes from capital T to 0. And this is precisely what we have seen here, right? We see that if the controls have the tendency to be very active towards the end of the time horizon, is because the control is simply reflecting a trajectory of the adjoint system where you start from some datum at time capital T and then you go down. Okay, very good. So let me do it more carefully. Okay, let me do it more carefully. Let me discuss the heat equation, and this is a way also of discussing classical optimal control for a heat equation in a more systematic manner. Okay, so let me take then a cavity capital omega, the heat equation inside the cavity heat capital omega, so some heat diffusion or some population dynamics, right? Some model in mathematical biology or some pollution problem, some contaminant that is diffusing inside this domain capital omega. This will be modeled typically by a heat-like equation. Let me just take the heat equation with constant coefficients 1. And now I control in small omega. So small omega is the patch where I am controlling. I could also control on the boundary as I was doing for the wave equation using multipliers. But this is also a very natural context in which the control is acting on the inside. I have placed some heater inside and I am regulating, right, the flow, right? I am regulating the temperature, the evolution of the temperature through the action on this heater, right? Collocated here in omega, right? Okay, very good. Now, I am doing it through some force, right? Some source, F, right? Which depends in principle on X and T, and that is, of course, acting here, right? In a small omega. Very good. So, of course, from the perspective of the Cauchy problem, I take here 0 boundary conditions to simplify the presentation so that, the exterior wall red is frozen, is 0 temperature, right? And I want to keep, this, chamber where we are living warm, right? And I have to do that through acting on this heater in a small omega. Very good. From the perspective of the Cauchy problem, there is no problem. If you give me an initial datum in L2, and you give me a force in L2 space-time, then there is a unique solution which is continuous in time and also gains some integrability of the gradient in space due to the regularizing effect of the heat equation, right? So this is a situation where we are dealing with an infinite dimensional, of course, infinite dimensional control problem, right? On which my goal, right, is in a given time horizon, right, capital T, to get close to some final target configuration, right? So, I mean, if it's true that is zero temperature outside, right? And after maybe 2 weeks of vacation, you go back home where the heating was disconnected, was off. Then when you will get home, right, the temperature will be very cold, maybe it will be like 12 degrees or so, right? Then you will turn the heating on so to warm the home up and try to bring it, maybe not in minimal time because this will use a lot of energy, but in a reasonable time, right? Bring it to a warm temperature of say 19 degrees where you can be comfortable at home, right? So this is the typical controllability problem, right? So this is a controllability problem. You want to reach a desired final configuration. Good. Now, of course, if you are an expert on PDs and all these techniques we have shown and many others like Fourier series and Kahneman inequalities and so on, you will, give a very precise, say, result about the controllability of this model, right? So you will handle this very, very carefully and in a sharp manner, okay? But if you are not, if you are just a practitioner, you will probably adopt an optimal control perspective. This is something we have also discussed. Anyhow, in case there is controllability, the controllability can always be achieved as a limiting process of an optimal control strategy, which is much simpler to apply, right? And penalizing the final target, right? So what is the most, say, traditional approach of optimal control to this problem? Is to say, listen, it's very simple. If you want to conduct this heat equation from the initial configuration to the final desired configuration Y star, and you need to compute the heat source F that you want to apply in small omega to reach this target, what you should do is out of all the possible F's in L2 of a small omega cross 0t, which are the admissible controls, right? You can allow all possible F's. I will tell you which one is the best. And the best is that you minimize this quadratic functional, right? In which you penalize two terms. This is a two criterion optimization problem. You penalize the control because you don't want the control to be too large. And you penalize also the distance to the target. For instance, in L2, these are the simplest topologies because you really want Y at time t to be close to Y star. Okay? You penalize the two nodes. Good. This problem, this functional is convex, is coercive because you see we have here the L2 node. Because the dependence of the solution Y on F is linear, this functional is also convex. Recall what we said. Be careful with the composition of convex functionals to claim the composition is convex. This is not always true, but certainly it's true that the composition of a convex functional with a linear one is convex. So this is also convex. So we have continuous functional, convex, coercive. In a Hilbert space, there is a minimizer, right? Okay, so there is a unique F minimizing the functional, right? Very good. Good. And we know furthermore that I could compute the minimizer of this problem by applying a gradient descent algorithm, right? I am on the frame of the gradient descent algorithm, and that in practice, this means that I am building an iterative map in which I solve the adjoint equation, then the state equation, and I adjust the adjoint all the time according to the residual of my control goal, right? So all this is systematic. And then when I precisely write, the optimality system, which is what are the conditions of, being the optimum, or if you want to, which is the same, what is just one step on this iteration of the gradient algorithm, you see that, as we said in the previous presentations, what you do first is you solve the red adjoint equation backwards in time, right? You plug the control P, you solve the Y forward in time, right? And then you adjust, the value of the adjoint at the time capital T out of the residual. And the residual here is precisely what is the gap to the target Y star I was given. But you see, as I anticipated before, that when you are doing so, of course, the control will be just given by the adjoint minimizing the system. The control then is equal to P, which is one solution of the adjoint. And independent of which solutions of the adjoint I get, as I said before, because this being the structure of the system, I know that the adjoint will have this shape. Why? Because this adjoint heat equation does, in the backward sense, precisely what the solution of the heat equation does in the forward sense, so that the P will be much larger in the end than it was in the beginning. So I will not see the Turnpike principle, okay? Actually, these oscillations we see here are related to the fact that, the minimization algorithm is exploiting to the maximum the properties of the functional, and then, out of the control region, there appear, high frequency oscillations, precisely as those, indicated by Tikhonov in his, say, highly oscillatory and not completely, say, unique solution of the Cauchy problem, right? So please keep this in mind. This is explaining the classical textbooks in partial differential equations like Fritz John or Evans. Be careful when we say that the solution of the heat equation is unique. This is true in a reasonable functional class of functions that are bounded and decay and so on. But if you allow functions that can be very, very large as infinity, there are other solutions that Tikhonov found, right? And that escape this uniqueness property. And then once you know these Tikhonov solutions exist, you realize that indeed, the control problem aims to get to them in order to increase the efficiency of the control process. Anyhow, I don't see the Turnpike in here. I really don't see it, okay? This process is not something like nearly constant to then be active to get to the end. So this process is really increasing the intensity of the control as you evolve, right? So it's like a trip in which you start very slowly, and then you realize that the time is less and less and less, and then you accelerate more and more and more and more until you get to the end in this very, infinitely rapid race, something that will be, of course, very dangerous or even illegal, right? Very good. Okay. So this is something we analyzed with Alessio Porretta in a paper published in same Journal of Control 8 years back, right? We said, how can it be that the Turnpike principle being apparently completely generic, right? We don't see it in the heat equation. By the way, I mentioned one application of the Turnpike principle is this, say, sonic boom minimization problem, because the time horizon is very long, right? But you see, the same happens, for instance, on the health system. If you have high blood pressure, you go to the doctor, the doctor will make the analysis of your blood and say, okay, yeah, you have high blood pressure, so take 1 pill per day and come back after 6 months and we will do an analysis, a blood analysis again. So how does the doctor treat you? They give you, a pattern, you know, for taking care of your pressure, blood pressure, and this pattern is constant. They tell you 1 pill per day for 6 months. I mean, the doctor could tell you, well, on Monday you take 1,1 pill, on Tuesday you take 0,97, on Wednesday 1,02. It will be too complicated. 1 per day is very easy to implement. So this is a constant control pattern, is the Turnpike, right? So the same when you look to the interest rate of the Bank of Europe, they say, okay, for the next 6 months, it's going to be 0.25. You know, the interest rate, the reference interest rate for loans from banks. Again, in the long time horizon, they set up a policy which is, you know, nearly constant. Of course, you cannot do that in an emergency, right? So if you have a heart attack, then you need to be treated in real time. But then the control time is not long, it's just very short, right? And then what they will probably do is they will put on your heart through some defibrillation mechanism, some kind of direct delta control, right? So you see that the fact that the Turnpike emerges and that you are allowed to use controls that are nearly constant depends very much on the fact that the time horizon is long. If you are given just a too short time horizon, you cannot use constant control. No. I mean, if you start doing a very gentle massage, you will not recover someone that is undergoing a heart attack. You really need to do a direct delta control. So you see that the time horizon matters. But here, in my discussion, I said, well, again, I don't see the role of the time horizon because the control is always given by the adjoint, and the adjoint really is behaving always in the same manner. It's true that it could be smaller in longer time intervals or larger, right, in shorter time intervals. But this is just a matter of scale. The behavioral pattern of the control is always the same and is not compatible with the fact that we are aiming for Turnpike, you know, patterns. Okay, so in this work with Porretta, we analyzed the same problem and we said, well, why is that true? Actually, if you see that here, you know, the Turnpike doesn't hold, right, and it does not. Well, I mean, I asked two colleagues and some of them told me, well, listen, certainly von Neumann and Samuelson, they were not thinking on PDEs, they were definitely working on finite-dimensional systems. That is true, right? But you see, even if I will replace this by a finite element approximation in which this minus Laplacian will become a matrix, high-dimensional matrix, the dynamics will be the same. So it doesn't seem that what, you know, the obstruction we encounter here is really related to the fact that we are talking about an infinite dimensional system. It's really related to the fact that, you know, the P equation is independent of the state equation, right? So really the fact that, you know, the P behaves simply according to the adjoint makes it impossible the emergence of the Turnpike principle, because the solutions of the heat equation in the adjoint sense always fulfill that. Good. Then we said, so maybe we should do something else. Maybe even though in principle, you know, in the control problem, apparently there were only two criteria, the size of the control and the distance to the target. By the way, I could penalize the distance to the target to force to get closer and closer to the target as in the controllability problem by using a large penalization here, right? That's fine. But again, this will not change if I have done that here, right? Sorry, if I have done that here, I will not have changed the fact that the Turnpike principle fails, because then I will have a multiplication constant here, but I will still have the P isolated behaving that way. It will be again a slightly different solution, but it will have the same pattern. So what we said, if we really want the P equation not to be completely independent of the Y, what we have to do is to not only penalize the control and the distance to the target, but also penalize the amplitude of the trajectory, right? And you could say, well, the minimization problem looks the same. It's just minimize with respect to L2 in a small omega cross 0t, dysfunctional, but now I have three criteria that I combine, right? One is distance to the target. That's perfect because this was the objective. Size of the control. This is natural because I don't want to consume too much energy in my control process. But here the add, right? So this is new, is that, you know, I add also the penalization of the trajectory. You might say, well, I don't think this is natural. I tell you, well, it's not that unnatural either, right? Because if you are going from, say, Changchun to Beijing, right? Well, it's true that you have to look for the Google Maps and look for the optimal trajectory, but in any case, you don't want to do two oscillatory patterns, right? So everyone understands that, I mean, this will very hardly be, you know, optimal. Of course, it could be optimal if you were, you know, crossing the, you know, the ocean or a lake area, right, where, you know, all this was, you know, occupied by lakes, and then the only chance you have is to go through this path in order to, you know, to be able to drive or walk on Earth, right? That's true. But in general, right, when you try to guide, you know, track, you know, a mobile object optimally, you will try also not to deviate too much with respect to what is more or less the straight line or the geodesic, in the sense that too high oscillations are hardly compatible with optimality, because in order to oscillate a lot, right, in order to oscillate a lot, this also takes a lot of time. Or if you want to, you know, not to spend too much time on this, you know, twisting oscillations pattern, you will have to drive very, very fast, and this will increase the consumption of oil. So in the end, eventually, it's very natural also to penalize the state. Okay, fine. Now, if you ask me from the optimal control perspective, can I do that? And then I tell you, yes, of course you can. Because this new functional, which is different from the previous one, because it's the previous functional written in black plus this extra term, this new functional is also continuous, convex, and coercive in the same Hilbert space. It's coercive because I have the square here. It's convex because, you know, y depends on a linear fashion on the control f. And it's continuous because whenever f is in L2, all these quantities here are well defined. This is just the classical PD, say, well-posedness elementary result. What is the only difference, which looks like purely algebraic, right, on this example? Well, the difference is now that because you are penalizing also, right, the state on the cost functional, when you look to the optimality system, you find here a y term. And say, well, this looks like tricky, right? So, and this is why actually when we do controllability, we don't use often this kind of, you know, functionals, right, to find the optimal controls, because then the adjoint gets, you know, combined with the state. And then the analysis of this system is more complicated, right? It was much easier to do it when there was a zero on the right-hand side. because then the adjoint equation was completely isolated, and I could just do my multiplier identities, integration by parts, Carnot transform, and derive the needed observability inequalities. Now, if you tell me that P is coupled together with Y, if I start doing the same, I will get Y everywhere. But Y is the state, and Y is coupled to the P, so everything will be much more complicated. So I don't really want to do this when I am doing the classical analysis of the observability problem. But you see, this is a fundamental theoretical result, right? So you have to separate what is the fundamental theoretical result telling you that the wave equation or the heat equation is controllable with the practice of how you actually compute the optimal controls and you implement them on the system. It's the same I said in the context of machine learning. I gave you, I will get back to this by the end of this lecture. I gave you a very complicated result saying that if you do a lot of zigzagging out of a neural differential equation, you can classify many points. I told you, this is a theoretical result. Is that important that you know? You know that everything can be done. What it doesn't mean is that in practice, right, the controls have to be as complicated as the ones I have built, because the one I have built were the controls for a configuration that can be extremely intricate. Now, in practical applications, oftentimes controls are simpler because, you know, you are not in the worst case scenario, right? I mean, it's like, you know, I mean, there are days that are very nice, days that are tougher in your life, but of course, you don't live every day in the worst possible scenario, right? Okay? You have to be ready for a difficult situation, but normal days are much smoother. Good. So what happens then? Then in this system, there is a coupling. And this is why if you have to apply the gradient descent algorithm here, you should be a little bit more careful, because you should initialize with a Y, then solve the adjoint, compute the adjoint, plug the adjoint on the state, compute the residual, and continue, right? But you have to initialize also with some Y. Before we didn't need to think on the initialization with the Y, because there was a zero on the right-hand side. So here you will have to initialize with a Y. Well, this is not that difficult. You could take zero control, just compute the solution of the heat equation, and start with this initialization, right? But you see that this obliges you in the implementation of the gradient descent algorithm on changing the first line on your algorithm, which is the initialization of the process. But this is not so relevant. This is just a technicality when you apply the gradient descent algorithm. What is more relevant here is that now this system is fully coupled. You cannot compute Y without P, but you cannot compute P either without Y. You have to compute the two of them together. But this is tricky actually, right? Because this is not a Cauchy problem. I have an initial datum for Y, but I have a final datum for P. This is not a Cauchy problem. I know there is a solution of this problem, because this is the characterization of the minimization of this functional. And this functional has a minimizer because of the direct method of the calculus of variation. So I know this system has a solution, but you don't know it out of the theory of semigroups. You know it because you are characterizing the minimizers of this problem, right? Okay, good. But anyhow, once you know that this system has a solution YP, and once you know that this is the minimizer of this problem, you wonder how it looks, right? And then if I write down how it looks, I see that the system is tricky, right? Because, you know, one equation is moving according to the first line, and the other, right, is behaving according to an unstable heat equation, right, that could be written in this way. So here I have a plus, I'm sorry. So here I have a minus, right? Here I have a plus, but here I have a minus. So this means that from the perspective of the Cauchy problem, in this system, there are both stable and unstable components. Actually, when you check the spectrum, this is what you see. Indeed, you know, this system, the spectrum of this system, when you take different, say, configurations for the small omega, will look like this or like this, meaning that on the complex plane, right, on the complex plane, the spectrum will have always two very distinguished components. One, which is on the positive side, that will be unstable from the perspective of the Cauchy problem. This is the one corresponding to the adjoint. And the other one that is stable is the one corresponding to the heat equation, which is evolving in the positive sense of time. And it's the fact that the two of them, right, are present, right, like in this explicit computation you can do when small omega is equal to capital omega, which guarantees that you have the Turnpike principle, right? So the Turnpike principle says that indeed, right, a system that is controllable will enjoy the property of Turnpike. But in order to enjoy the property of Turnpike, you need to consider controls which are not simply the controls we were considering before, the ones of minimal norm, but rather the controls that make a compromise between the minimum of the norm of the control and the minimum of the norm of the state. Right? So then I repeat, the Turnpike principle will occur, and this is what I am drawing here, right? This is the Turnpike principle. It occurs, but it occurs only if I consider trajectories, control trajectories, which are achieved as minimizers for, you know, a compromise between the state and the control. Okay. Now, how can we proceed to the proof and the analysis of this? I just give you quickly the algebra. How you proceed with the Turnpike principle? What is the practitioner approach to the Turnpike principle? It says, okay, assume you give me sorry, I have lost now the connection of the pencil. Okay. Assume you give me now, my pencil was out of battery. Sorry, I will need a few seconds to recharge. Assume you give me this evolution control problem. How do I proceed? I say, okay, you give me the evolution control problem, and for instance, just an optimal control problem in which I am minimizing the functional J, penalizing the control and the state. I have a optimality system. I can also chop off time, right? So remove time, and I say, now I forget about the time evolution. I just consider the steady state trajectories, which are independent of time. So the time derivative of the system disappears. This becomes an static system AX equal to BU. And of course, on the time evolving optimization problem in which I am minimizing an integral on time, now it doesn't make sense to talk about integrating on time. I just take the static equation, the static functional, and I minimize that one. There will be also a minimizer, and when I look to the characterization of the minimizer through the optimality system, what I see here, down here, right? What I see down here is that this is the same optimality system as for the evolution problem, but on which I chop off the time derivative, right? So you say, well, this looks nice because, the optimality system for the evolution problem and the optimality system for the steady state problem look the same. So I have time evolving problem, time evolving control, time evolving optimality system characterizing the optimal control, and in parallel I have the steady state system the steady state control independent of time, and the algebraic independent of time, right? Optimal control condition, the optimality system characterizing the optimal control, right? Then our theorem says, this is what we did with Porretta, extended also to the finite dimensional systems, both parabolic and hyperbolic in that paper I presented here, right? For simplicity in the finite dimensional case, we said, in order to guarantee the controllability, right? Sorry, in order to guarantee the Turnpike principle, you need to, optimize the control in a way that not only you have the controllability property for AB, which is important to guarantee the controllability of the system, but you have the analog, involving the C being the operator you are plugging here on, the functional you are minimizing on the state. Why? Well, because we have seen if C is equal to 0, if you don't penalize the state at all, like in the heat equation, you don't get the Turnpike. You need to penalize the state enough, right? And what does it mean to penalize the state enough? It means that the C operator that you are getting here in the adjoint equation will play the same role as B does on the state equation for the controllability property. So in some sense, right, you see that the Turnpike principle requires that you penalize enough the criterion that you are minimizing to compute the control, and this enough is measured in terms of the same kind of rank condition as B has to fulfill in order to guarantee the controllability, right? There are several proofs for this principle. Maybe the simplest is that you think on, control problems in longer and longer and longer time horizons. If you do this, then you will say, oh, but there is the classical infinite horizon, say, linear quadratic regulator problem, right? So in infinite time, I know that the optimal trajectory is given by the Riccati feedback operator, and I know it decays exponentially as t goes to infinity. This is true. Then what happens when you are taking time to be long? Well, you are chopping off this trajectory, right? And therefore you see some tendency towards stability plus a small final arc, right? That, you need in order to, reach the terminal condition of the adjoint heat equation. So this is the linear theory. In the nonlinear context, there is still plenty to be done. We observe that, the Turnpike principle is very robust. You observe it computationally when you do, nonlinear control systems as well. But we don't yet have a complete theory showing that indeed the Turnpike theory also applies in the nonlinear context. We can, of course, do a small, this is what we did in this paper with Porretta back in 2016, where we say, well, I mean, if you have the Turnpike theory for the linear problem and you do a small nonlinear reformations, you keep it. But definitely, the simulations show that the effect of the Turnpike is much more universal than what we can actually prove, right? And this is the Turnpike principle. The Turnpike principle says, now, if you are allowed to control the system in long time, right? So if someone tells you that by tomorrow you have to write a 25 pages article and starting now, I mean, you cannot do it Turnpike, right? You have to do it in just one evening. So drink coffee or tea, don't sleep overnight, and try to get your manuscript finished. But, if you have to do it by the end of August, I tell you, well, just write 1 page per day. If you write 1 page per day, we are today, July 24th, by August 20th, you will be over. You will have your 25 pages written, right? And then you still have 1 week to revisit the manuscript. So just 1 page per day. This is the Turnpike principle, okay? And then the Turnpike principle says, compute the optimum of the steady state problem, right? So first iteration, chop off time, consider the time-independent control problem. If you are in a PDE context, this will become an elliptic equation without time. Computing the optimal control for the steady state problem is much simpler because there is no time dependency. It's just a static problem. And then build an optimal or quasi-optimal trajectory by just, gluing the initial position to the steady state control. Keep the steady state control, which is very simple to maintain because it's independent of time. You can let simply the automatic driver to do it. And then when you are close to destination, exit, the highway to get to the control. This is the arc that needs A, B to be controllable. And this is the arc that needs, the adjoint system to be controllable. This is what the Turnpike principle says. And here I am denoting this red arc, right, which is not optimal completely, is slightly suboptimal, but it's something that it can be also very beneficial in practice, right? So if you, in the steady state functional, you had such a configuration, right, where clearly the global minimum is over here, but there is also a local minimum. If you will apply the Turnpike principle with the local minimum, that will be fine as well, except that it will be slightly more expensive, right? So this is like there was a highway and nearby there was another road that was not as fast. Of course, if you take this one, you will pay a long, a little bit more of time, but still it will be fine to do it, right? So this is to say that even for problems that are not, convex in the steady state context, you can still apply the Turnpike principle with any local minimizer and get trajectories that are doing nearly optimally, right? Of course, you see that, in this case, right, if the distance to be, for destination is very long, of course, it will always pay off to go, to the global minimizer. But this is what you see when you take the taxi, in cities like Beijing, where you have many rings, right? And you are taking the taxi in the evening from here, right, to here, right? So if you are doing it in the evening when the downtown is completely empty because people, in the middle of the night, right? Everyone is at home, sleeping. So maybe the taxi driver will do this, right? But if this is during the daytime, right? If it is during the daytime and the downtown area is so busy, probably the driver will do something like this. Will try to exit the downtown area as soon as possible, get to the second ring, and then drive you in this way to destination. But if the second ring is also very crowded, so maybe the taxi driver will get to the third ring, will evolve along the third ring, and then it will drive you to the destination. But even if the third ring is very busy, then it will go to the fourth ring and will do this. So you as a passenger, right, will be very surprised. You say, oh, but why are you taking me in this direction while I am moving in this direction? You will complain. Maybe the taxi driver doesn't know the city. Maybe he has just a new driving permit and he doesn't really, he doesn't orient himself well. Or maybe he's cheating me by building an artificially long trajectory. No. It's not this. It's that if you really want to minimize time, if the traffic in the downtown area is very crowded, this could be the optimum from the perspective of minimal arrival time. And this is precisely what we are doing here. Every time we take one of these rings, we are doing a Turnpike, right? And there could be several, depending on the local, say, minimizers of the steady state function.